Hello, we will kick this off with what I call topic 0 because it's not in the curriculum or anything, but it is in your book. Okay, so this is topic 0, physics fundamentals, also known as working as a physicist. Okay, so this is where we will discuss standard units in physics and estimation problems, and these concepts, especially units and such, both base units and derived units, come up over and over and over again in unit 1, 2, 3, all the way up to 6. Okay, so let's start with the first topic, which is standard units in physics. Okay, so this is information you need to know. You absolutely need to know. Okay, so physics, I keep repeating this because it's important to me because I studied theoretical physics for my PhD, but physics is primarily an experimental science. Okay, which means that we need to take measurements to understand how a physical process works. When I say I studied theory, this means that theorists in general study the world mathematically, okay? So they come up with equations and they try to see whether those equations apply in nature, okay? But physics is experimental, so for any law to become a law of physics, it needs to be verified experimentally. So for example, Newton laws have been experimentally verified over and over and over again over the past, 3 centuries or something. Same with Einstein's relativity. Okay, I mean, Einstein's relativity has been around since, I think it was 1905, when special relativity was introduced, etc. So in order to understand the physical world, measure quantities, and so on, we need to take measurements, okay? And those measurements we express, again, I'm gonna make a big effort to make good letters, but it's not my major skill. So we express measure quantities using appropriate units that come in 2 varieties. Base, okay, and derived units. And let's go see, let's start discussing units with base units. So base units are used to express fundamental or intrinsic in nature, properties of objects. So things such as length, the mass, the amount of quantity, what else? Temperature, etc. So these are all fundamental properties of objects, okay? Meaning that they cannot be expressed in terms of the other quantities. So, for example, length cannot be expressed in terms of mass, okay? And length is an intrinsic property. So, for example, my height, which is a length, right, is special to me. I mean, it's an intrinsic quantity, okay? So there are only 7 base units in nature. So let's list them and discuss them a little bit. So you need to know them, okay? That's the thing. So there are only 7. So base quantity, I'm gonna make a table with listing the base quantity. Actually, let me leave some space because my tablet screen is not too large. Wait, what did I do? Okay, let's move this down there. And let's move this down up there. Okay, that looks good. So, base quantity. So here we're gonna list things like mass, time, etc. Unit name and unit symbol will be recorded in this table, okay? So, 7 base units or quantities, okay? Mass is measured in kilograms, okay? That's the name of the unit or unit used to measure mass, and the symbol is kg, okay? Time is measured in seconds, and the symbol is just S. Electric current is measured in, actually, before we mention the current, let me write mass, time, and length, okay? And I will explain why. I have these 3 listed first. So the unit name is the meter, and the symbol is M. Then the electric current measured in amperes, and the unit is capital A. Temperature is measured in kelvins, not Celsius, okay? Kelvin, capital K, okay? The amount of substance is measured in, the unit name is mole, and the symbol is just mole without the E. And then the light intensity is measured in quantity called candela, measured, and the symbol is CD. Okay, all of them are equally important, obviously, but these 3 appear most frequently in unit 1, okay? And the other comment I have is that this last one, the light intensity, is very rarely used in physics. I mean, I've never really encountered it after so many years of studying physics. It's the only one time when I was an undergrad student, okay? So the first 3 are used in problems that deal with mechanics, okay? Like motion, forces, moments, these kind of things. Then electric current is used in circuits and such. Temperature is related to thermodynamics, and so is the amount of substance, the mole, and the amount of substance is also used in nuclear physics, okay? So just a broad overview, okay? But the only thing you need to remember is that there are 7 base quantities, and any other quantity in nature can be expressed in terms of these 7 quantities, okay? So let me write a brief note before we move on. So note, current is defined as charge flowing in a circuit per unit time. So it doesn't appear to be fundamental. It appears that charge should be the fundamental quantity, but current was chosen, okay, to be the fundamental quantity. So current was chosen as the fundamental quantity. Okay. Thus, charge is now current times time. Okay. So thus charge is a derived quantity. And we haven't defined what derived means yet, but we will do so, I'm sorry, in a moment. I'm looking through my notes. Okay, I'm gonna confuse myself with this unit 1, maybe, because I'm using 2 sets of notes. One from the time when I actually taught the class in a classroom, in a proper classroom with students and so on, and another set of notes that I developed for these YouTube courses. So, okay. Another note is maybe that the kilogram has this prefix here, kilo, which means 1000 grams, but we will get to that later. So let me erase this for now. Okay, so by discussing the charge, we kind of already discussed what a derived quantity is, so, or derived units. So derived units are used to express dynamical properties of objects. So what do we mean by dynamical? Things such as speed, energy, power, momentum, and so on. Okay, so speed expresses motion, and so does energy. Power expresses the rate with which energy is flowing. Momentum expresses the rate with which an object moves, and so on. Okay, so actually momentum expresses the rate with which a force acts on an object formally. So derived units are used to express dynamical properties of objects. Okay, they usually require multiple measurements. And what I mean by that is that, for example, speed is length per time. So to measure speed, you need to measure both length and time. So you have to keep track of 2 quantities at the same time. Okay, but okay, in modern living, even your cell phone can measure speed nowadays, and only one measurement is needed. But you get my point. Like, you need to measure to keep track of 2 things to measure speed, and the same goes for other derived quantities. Okay, some derived units have special names. And perhaps the most popular is the Newton. Okay, 1 Newton is 1 kilogram times meters per second squared, right? Because F, force, is mass times acceleration, right? So mass is measured in kilograms, and acceleration is measured in meters per second squared, and 1 kilograms times meters over second squared is also known as 1 Newton. Okay, so but not all derived but not all derived units have special names. For example, momentum, P, is m times v, and it's just measured in kilograms times meters over seconds, okay? Doesn't have a special name, okay? So the bottom line is that derived units are built combining base quantities. Or actually, let me write base units, okay, to be consistent. Okay, so derived units are expressed in terms of these 7 base units, okay? And these 7 base units are independent of each other because, as I said earlier, length cannot be expressed in terms of time or mass or current or something like that, all right? Now, let's go list some popular derived quantities, derived units. Will I need a clean page? Let's do a clean page. So I'm going to create a table again. Derived quantity will be the first column of this table. Unit name will be the second column. Unit symbol, unit symbol will list the symbol, and base unit equivalent will list what the unit symbol corresponds to, okay? You will see in a moment. So let's make this table. All right, so force is the first one that we already discussed. The unit name is Newton for Isaac Newton. The symbol is N, and the equivalent base quantities are kilograms times meters over second squared, okay? The second one, which is also maybe equally popular, is energy or work, okay? By the way, work and energy are the same thing. I mean, they express energy used in a process, okay, or an energy that an object moving possesses, and so on. So this is named after Lord Joule. I think he was a lord. I'm not 100% sure. Check. So the unit symbol is Joule, and the equivalent base units are kilograms meter squared per second squared. And how do you know this, by the way? Because remember that kinetic energy is 1/2 mv squared. 1/2 does not have units. I mean, it's a constant, right? But the mass is expressed in kilograms, and velocity squared is meter squared over second squared. So that's how you know the base units equivalent, okay? Let's erase that. And let's move on. The next logical step is power measured in watts, expressed with the symbol capital W. And this is energy per time. So the unit will be kilograms meter squared over seconds cubed, right? Then frequency has the name hertz. Okay, Hc. And the unit is just seconds to the -1, okay, because it's 1/time. And then charge, we already discussed charge. The units are coulombs, expressed with capital C, and they correspond to amperes times seconds, okay? Remember, amperes is a base quantity, okay? Next one is voltage. It also has a name, volt, after, I think his name was Volta, the Italian guy who experimented on frogs. So he passed electricity onto frogs and the legs moved, something like that. So go check it out. The unit symbol is capital V, and the units, okay, hold your breath. It's kilograms, meter squared, seconds cubed, and amperes, okay? And the last one that I have here is the resistance, the electrical resistance, okay? Is measured in ohms. The symbol is capital omega, the Greek letter, and the units are kilograms meter squared over seconds cubed amperes squared. Okay, this took a while. So these are some fundamental, not fundamental, I mean, sorry. These are some popular derived units, okay, that's a proper name. And let's move on, okay? So we have the definition of what base quantities are and what derived quantities are. So the next thing we will discuss is how to express really large or small measurements. So let's write this down. Expressing very large or very small measurements. And this is something that this is used with both base and derived units. Okay, and the way to do that is to use prefixes. Okay, so what do we mean by large or small quantities? So for example, the distance between my hometown and the next large city is 100 kilometers, right? But 100 kilometers is 100,000 meters. So you're not gonna say, you don't really use meters to measure distances between cities. You use kilometers, right? So that's the idea. Or the dimensions of a cell, like an animal cell or maybe a plant cell, is if I'm not mistaken, is in the order of magnitude of micrometers, which is 10 to the minus 6 meters. So you cannot use meters, you need to use micrometers. Okay, so that's the idea. So let's discuss the most common for large measurements. So most common for large measurements. So those are, okay, I'm gonna list the factor, the name, and the symbol. Okay, so for the factor of 10, the name is deca and the symbol is dA. Okay, it's very rarely used. Then 10 to the second, the name is hecto and the symbol is H, also very rarely used. But then we have a very popular one, 10 to the third. The name is kilo and the prefix is K, lowercase k, okay? This is very, very frequently used. Another popular one is 10 to the 6, which is the mega with capital M. Okay. Next one is 10 to the 9, giga, and the symbol is capital G. 10 to the 12, which is tera, with capital T. And 10 to the 15, which is peta, with P, okay? So these are the most commonly used, okay? Now let's go talk about small quantities. So again, the same table, factor, name, and symbol. So 10 to the negative 1, the name is deci, and the symbol is D, very, very rarely used. Then 10 to the negative 2, name is centi, and the symbol is C. Then 10 to the negative 3, the name is milli, symbol is m, 10 to the negative 6 micro, and the symbol is the Greek mu, okay? 10 to the negative 9, the name is nano, and the symbol is n. 10 to the negative 12, the name is pico, lowercase p. 10 to the negative 15, the name is femto, and lowercase f is the name. And finally, 10 to the negative 18, the name is atto, and the symbol is a. Okay, so the most commonly used in this case are these ones, okay? So these are the most common. All right, so it's a bunch of definitions, I'm sorry guys, but we have to go through this, okay? So, okay, remarks. For derived units, always convert the prefixes to the base quantity. So what do I mean by that? For example, they told you that something covered the length of 10 kilometers in a time of 6 hours. So what was the velocity involved? Length over time is 10 kilometers over 6 hours, but we have to convert kilometers to meters, so 10 times 10 to the third meters. And 6 hours, 1 hour has 60 minutes and 1 minute has 60 seconds, so we have to convert to seconds, okay? So this is what I mean by converting to base. So the velocity is 0.46 meters per second. So if they tell you that this is, I don't know, a snail that covered this distance in 6 hours or something, then you can find the average energy, for example, I don't know, something like that, if you know the kilograms. But you have to get rid of prefixes when you work with units, okay? So, and another remark, okay, that's the first one. The second one is that the kilogram is weird. Oops. I'm sorry. Is weird in that it already comes with a prefix. Okay, so you have to be careful because 1 kilogram is actually 1,000 grams, but then 1 milligram, for example, is 10 to the negative 3 grams, therefore is 10 to the negative 6 kilograms, okay? You need to be extremely careful with that. So that's all when it comes to units. So the next thing we will discuss, which will cover topic 0. Remember, I called it actually topic 0, okay? So the next thing we need to discuss is estimation, okay? And you will see what I mean. So the next thing in topic 0 is estimation. Which means kind of like having common sense when you work with physics. So for example, if they ask you to calculate somehow the weight of, the mass of a human, and you find that mass to be 2,000 kilograms, that's obviously wrong. You should have an idea about what the average weight of a human is, something like 60 or I don't know, 70 kilograms or something like that, okay? Or if someone tells you the height of a house, okay? And you found the height of a house to be 1 kilometer, which is 1,000 meters. That's absurd. That's crazy. So the height of a house is, I don't know, something like 3 meters, maybe 4. maybe 2.5 meters, something like that. So you have to have a sense of what's going on around you. So when working with calculations, in physics, it's good to have a sense of the order of magnitude of quantities. Okay, so if you find, for example, the speed of an object to be 4 times 10 to the 9 meters per second, you need to automatically be able to tell that your calculation is wrong, since c is 3 times 10 to the 8 meters per second. That's the speed of light, and that's the highest speed you can have in the universe. Okay, so this is what I mean by estimation. Okay, so it's good to have some rules of thumb, and also estimation can be used to estimate quantities. So for example, how many golf balls can I fit in my room? Okay, so to calculate that, you have to have a sense of what the volume of a room is. So for example, the room is like 3 meters high times 3 times 3, okay, maybe 27 cubic meters, okay, and maybe I don't know, a golf ball has a radius of, I don't know, 5 centimeters, and it's a sphere. So the volume of a sphere is 4/3 pi r cubed. So by dividing these two quantities, you should be able to find how many golf balls you can fit, and so on, okay? And we will see a problem in a while, but let me give you a few more tables before we move on. So examples of things that you have to keep in mind when you work in physics. So some benchmarks for length are, for example, 1 times 10 to the 13 meters is the diameter of the solar system, okay? Then 1 times 10 to the 11 meters is 1 astronomical unit, which is the distance between the Earth and the Sun. Then 10 to the 4 meters, for example, is the radius of a city. Okay. Then about 2 meters is the height of a human. So let's write human. And then about 10 to the negative 5. Oops. So about 10 micrometers is a cell. Okay. A human cell or a plant cell or whatever. 10 to the negative 10 meters is the radius of an atom, and 10 to the negative 15 meters is the radius of a nucleus. Okay, so in terms of lengths, these are good benchmarks to keep in mind. Okay, now in terms of mass, so some popular masses, okay, some benchmarks are 10 to the 30 kilograms. That's the weight of the sun. Sorry, the mass of the sun. I'm sorry. 10 to the 24 kilograms is the mass of the Earth. Okay. About 100 kilograms. I know it doesn't sound flattering, but okay, let's let's say 100 kilograms is the weight of a human. Okay, it's crazy. Maybe I should write like 70. It's more realistic. Okay. Then about 10 to the minus 27 kilograms is the mass of a proton, and 10 to the negative 31 kilograms. Notice that it's about 1,000 times lighter than the proton is the electron. Okay. And okay, these are the benchmarks. And let's go talk a little bit about this estimation, and especially Fermi estimation problems. Okay, so Fermi was a famous theoretical and experimental nuclear physicist who worked at the University of Chicago about 100 years ago. He was one of the pioneers of nuclear fission, and he was the first to create a nuclear reactor, and so on. Go look him up. He won a Nobel Prize in physics and so on. So Fermi estimation problems are famous in physics in that these are problems in which you estimate the order of magnitude of a quantity. So Fermi estimation problems are order of magnitude estimation problems. Okay, so for example, how many basketballs can we fit in a room? Again, so the volume of a room is about, I don't know, 5 times 3 times 4 meters, so 3 meters tall. So the height is 3 meters, the length is 5, and the width is 4, something like that. So that's 60 cubic meters. Okay. Now for the basketball, let's say that the radius is 10 centimeters, which is 0.1 meters. So V of the basketball is about 4/3 pi r cubed. That's the radius, the volume of a sphere. So let's say 0.1 cubed meters cubed. So that's 4.2 times 10 to the negative 3 cubic meters. So the number of balls is equal to the volume of the room over the volume of a basketball, because if we divide these two, we get a number, right? So that's about 14,000. Okay, that's a lot of basketballs. And let me show you another popular estimation problem. So what is the mass of air on top of our heads? If the atmospheric pressure is 101.3 kilopascals. Okay, so how are we gonna do that? So the answer is you have to multiply. Remember that pressure is force over area, right? So if we multiply pressure with area, we will find the force, and then force is m times g, right? And that's equal to P times A. So the mass is P times A over G. So what's the area of a human? Let's say if we think of the human as a cylinder with radius 40 centimeters, which is 0.4 meters, we can say that, okay, pressure times area is 101,300 newtons per meter square, which is 1 Pascal. Okay, that's another derived quantity, by the way. Okay, so 1 Pascal is 1 Newton per square meter. Okay, and then the area is pi times 0.4 squared. So this is approximately equal to 51 kilonewtons, so 51,000 newtons. But F is m times g, so mass is force over g, so 51,000 over 9.81 gives you 5,200 kilograms. Okay, that sounds quite a lot, but I think it's about there. Okay, and I think I will stop the video here because it's a good point to stop, because we covered the zeroth topic. Okay, which is nevertheless very, very important for Unit 1, but also Unit 2 and all the way to Unit 6. Okay, so let me know what you think about these videos. Like, subscribe, and so on. And if you have questions, let me know in the comments. See you in the next video. Bye.